All right, so let's do this first set of the basics on significance tests. So it says lesson 9.1, day one at the top of it. We're really just kind of checking to see, do we kind of get the idea of this? And then we'll do the day two, which is actually all done in one day here. But it's the second worksheet that you'll see attached to your syllabus there. Okay, first one here. See how you do on this. So as we read through this, right, so I want to think about, so significance testing, like we saw in the notes, was I need to see a claim, and then I want to see what is suspected if that claim is false, right? But then we are going to derive everything as if that claim is true, and then see what kind of p-value we get, right? So those are kind of the big parts of it. Let's see if we can break this down. All right, calcium is a vital nutrient for healthy bones and teeth. National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is this true? All right, so here's what I want you to just take a note right here. 1,300 milligrams, that is what they have put out there as the main claim. That's what is supposed to happen. That's the recommendation. And then look, we can even get the suspected, not getting enough calcium. And then here they also put in a keyword for us, on average. So that way I can know that, am I talking about means or proportions? I'm talking about means. Is it true? State appropriate hypotheses for performing significance tests. Be sure to define the parameter of interest. So we're going to think about the parameter of interest here. The parameter of interest for us really is the average amount of calcium intake, right? So that's what we're after here. So let's kick this thing off. Null hypothesis. Remember, we always use this notation, H subscript 0 or subscript null. We call it null hypothesis, the initial hypothesis. We're going to say that the mean, the initial claim, the mean, it should be 1,300 milligrams, right? Now, there might be fluctuation from person to person, but it should average to about 1,300. And then what is suspected? That is our alternative hypothesis. Well, we suspect that the average is going to be not getting enough calcium. Let's go less than 1,300. Now, I want you to just recall that we always need an equal sign with our null hypothesis, and we will always do a straight inequality sign, never an equal sign with our alternative hypothesis. Right, now you sometimes on the null hypothesis, you'll see sometimes a greater than or equal to, or a less than or equal to, but it will always have the equal part because we have to have the equal part to help us out with that. Okay, there it is. Check what you got, see if we got that. If you really want to, I mean, truly, we should really put our units here, milligrams, because they do have units. We're talking actual numbers here. All right, let's move on. Researchers decided to perform a test using the hypothesis stated in number 1, so using our hypotheses there. They ask a random sample of 20 teens to record their food and drink consumption for 1 day. Researchers then compute the calcium intake for each student. Data analysis reveals that on average we have, so check this out. And remember, this is why notation is super important. They say that the sample average was this. So we are going to use this to try and fight this claim right here. So that's our goal. We have a sample and we have a claim out there. Here the claim is the true proportion is 1,300. I got 1198. Is that too far off? That's actually what we're testing right now. And it comes with a standard deviation. Researchers performed a significance test and they attained a p-value. Right? So again, from the notes, remember what p-value is. Explain what it would mean for the null hypothesis to be true in the setting. If the null hypothesis was true in the setting, then truly the average calcium that people are getting is 1,300. That people are getting, teenagers are getting the recommendation. That is what would be true if the null hypothesis is true. Okay. Now here's the p-value. Remember p-value, and we say the p is roughly 0.14. So here's my interpretation of this. About 14% of the time we would get a sample average of 1198 if 1,300 was the actual amount. Okay, so here's the key to it. 14%, that's the p-value. 14% chance, 14% chance of getting a sample like the one that we got, or more extreme, actually. That, right? So I should actually say, or more extreme than this. So then you kind of ask yourself, always with a p-value, what does that really mean to me? Well, if I said you got a 14% chance of winning the lottery, would you play the lottery? You're going to say, yeah, sure, because there's a really good chance that I can win that, right? That's 14% is really good, right? I mean, it's not great, it's not 90%, but thinking about lottery, instead of 1 in 1 billion or 1 in 1 million, you got a 14% chance. Yeah, I'm going to play the lottery. There's a really good chance I can win this thing, right? So there's a chance, right? You're within the chance there. So 14% is just saying that, yeah, you should get an average like this, 1198, if this is actually true, 14% of the time. So, it can happen by chance. It actually can, right? It's not as rare as you might think, right? So that's kind of what it means. So then, what do we do? What conclusion will we make at the alpha equals 5% level? Remember, when we said the alpha, we call this the significance level. So here's the idea, again, from the notes. We say if my p-value is less than the alpha value, then it is an automatic. Then we reject the null hypothesis. But if my p-value in this case is greater than, since it's greater than this, what we want to do, we're not going to reject the null hypothesis. We would fail to reject the null hypothesis. Okay, now this is going to be something we got to wrap our heads around. We're not going to accept it. We're just saying we did not find evidence to reject the null hypothesis, right? So remember, going back to the notes, my main idea is I want to reject the null hypothesis. I want to reject it. So I'm going to use my sample to see if I can find that evidence to reject this. And I either can reject it, or I am going to fail to reject it, but I'm still not going to accept the null hypothesis. I'm just going to fail to reject it. All right, there's your first worksheet right there. Let's move on to the second worksheet. Second worksheet is going to be a little more into the errors pieces of this thing, right? Okay, so let's look at this real quick. So manager of fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on the store records, the proportion of customers who have to wait longer than 2 minutes was this, right? So 63% of customers had to wait longer than 2 minutes, right? Okay, so to reduce the proportion, the manager assigns an additional employee to drive-through orders during the next month. Manager collects the random sample 250 times and finds a p-hat value. All right, so now we got a p-hat value. So now, remember, just like the other one, we're going to see, does my p-hat value give me evidence to reject that, right? Now, since we were hoping to reduce the wait time, my alternative hypothesis is going to be less than the current wait time. We're hoping that the employee change something, right? We call that an experiment. We'll talk through that later, how that actually goes together. Right now, we're looking at the logistics of the calculations. All right, here we go. Describe a type 1 error. Remember, type 1 error is when you reject the null, but you shouldn't have. Type 2 error is when you fail to reject the null, but you should have. Okay, so those are the different types. So let's try this. I'm going to put it over here. Type 1 error. Okay, describe it in the context. Type 1 error is when we say the proportion of customers who wait longer than 2 minutes is less than 63%, but find out it's still 63% of the customers, right? So that's a type 1 error. When we reject the null, we say we reject it, right? So watch, I'll do this with colors up here. We reject a null and say the alternative, and then find out, whoops, the null was actually true, right? So that's a type 1 error. Let's talk type 2 error, right? Let me kind of put it over here. Type 2 error is the opposite. So type 2 is when we say the proportion of customers who have to wait longer than 2 minutes is still 63%, but find out it's actually less than 63%, right? So type 1 error is essentially saying we believe it's working, adding an employee speeds up the time, but it actually doesn't. That's type 1. That's really kind of what's happening there. Type 2 error, we're saying that I added an employee and it didn't do anything, but then come to find out it actually did speed it up, right? So that would be the two types of errors. Remember, those are errors because you said one thing and you found out something else was actually correct. That's called an error. Which type of error is more serious in this case? So here's the deal. I'm not going to write it all out, but here's what I'm going to say. I think type 1 is a more serious error. Why? Because we think that adding an employee is reducing the amount of time customers have to wait, but in fact, it has not changed anything. So I still have customers who are mad because their order is taking too long, and I'm paying an extra employee. That's a more serious case, right? Because type 2, think about that. I added another employee, and I don't think anything is changing, but then come find out that it actually is speeding up the process, right? So type 2, you probably feel disappointed after a certain amount of time. You're like, nothing is working here. It's not helping, but it actually is. But here, type 1, I think it's a little more serious, is you think something's actually working, but it's actually not, right? So type 1, I believe, is more serious. Based on your answer to question 2, do you agree with the company's choice of an alpha of 10%? Why or why not? Right? So if I go on, a manager performs a test following an alpha of 10%. So here's the deal. So the probability of making a type 1 error is always equal to our alpha level. So in this case, it's equal to 10%. So there's a 10% chance that we make a type 1 error. So I'm going to say, you know what? No. If I think a type 1 error is bad, then reduce my alpha. I would probably say alpha at 5%, or maybe even go alpha at 1%, right? Right? Because if I don't want to make a type 1 error, reduce your alpha, because type 1 error is directly correlated to your alpha level. Okay, and then let's look at number 4. The p-value of the manager's test is 0.0385. Interpret the p-value. So just like our other problem here, here's what we'd say. Let's call that, I'm going to say p-value. I'm going to just go ahead and change it to what it is, 3.9%. So let me say this. So just go ahead and listen to it, and then pause it, rewind it, and listen to it again if you need to hear this again. But there is a 3.9% chance of getting a sample with a p-hat value of 0.576, 3.9% of getting this sample or more extreme if the p-value is actually 63%. Okay, so there's a 3.9% chance of getting the sample that I got or more extreme if this is true. So what does that mean? That's not very often, right? That 3.9%. Okay, now think about it. If you're winning the lottery was 4%, would you play? I mean, some people would probably still say, yeah, it's the lottery. 4% is still pretty good, but still start thinking. Now, as my percentage gets super small and we get closer and closer and closer to 0, we have less faith that this is actually still true, right? Based on this right here. This right here, it depends on how often I should get one of these. And the less often I should get this, the more suspect I am of this number. Okay? So that's the p-value, right? So you're going to be asked to do some of those things. And then finally, how do you find p-values? Let me just kind of do a real quick, just so you know when you see this on Khan Academy. Let's say you had, let's just give you a nice perfectly symmetric piece right here. Let's say we had, let's just add one more just to keep this nice and even. Let's say we had a sample of 10, right? So p-value is always about finding where the middle is, right? Or whatever number it is that they have, right? So let's say that this is number 5, this is 6, this is 7, so this is 4, and this is 3, right? And then let's say that they mark this as like, hey, this is the center of 5, okay? And they say, what is the p-value of the value 6? Okay, so what I'm going to do, I'm going to find the value 6, and I'm going to mark off that area, right? So I'm going to literally count how many values lie at 6, or more extreme, all the way to infinity, however many I can find there. Well, what we'd find here is my p-value, since I can count this, is 3 values are at 6 or more extreme over the 10 values. So I might say my p-value is 30% or 0.30. So that is p-value, right? So it's where your value is, where your sample is, or more extreme. So if I ask for the p-value of 4, we would look at 4 or more extreme. So you would be looking at this side now. Now that would give you the exact same p-value, but it's always away from the middle. P-values are away from the middle, more extreme. All right, so don't kind of go over the middle when you're looking at what values do you count. All right, so there you go.